Very good afternoon, sir.
Yes, sir. Proceed. Good afternoon, sir. Your voice is audible.
Yes, sir. Very good afternoon, one and all. I welcome you back for the second session of the today's FDP. Today's session, we have with us such a resourceful person, Dr. Pradeep Jain. He is working as an associate professor in Ajay Kumar Garg Engineering College, Ghaziabad. His working experience is 20 years of teaching experience. His specializations are CAD/CAM, robotics, artificial intelligence, and additive manufacturing. His qualification: PhD, NIET Kurukshetra, Haryana, ME CAD/CAM in NIT Allahabad, Uttar Pradesh. He completed mechanical engineering BE in GEC, Rewa, Madhya Pradesh, and his publication, he published 30 papers in international journals and conferences. He published 2 books also. He completed 10 industrial sponsored projects. Recently, he got patent for 3D printer. Presently working on AKGEC sponsored project Metal 3D printer. Welcome you, sir. Once again, I welcome you, sir.
Welcome, sir. Sir, please, आपका mic unmute कर दीजिए sir.
You are audible.
Okay, now can you?
Yes, sir. You are audible, sir.
Yeah, I'm audible. Thank you, Mr. Sarvan, for a nice introduction. Okay, just delay due to some connectivity problem. Okay.
No issues, sir.
Okay.
Okay, कोई issue.
Can you see the slides?
Yes, sir. Okay. Yes, sir. Visible, okay. Sir.
Okay. So welcome to all the participants, and it's my pleasure to share my views about the rapid manufacturing, additive manufacturing. Okay, Professor Rajkumar in the morning session already cover almost all the process chain and processes about this additive manufacturing. Now I will discuss what is this rapid manufacturing basically. So there is a different name for this rapid manufacturing. You can say like rapid prototyping, additive manufacturing, 3D printing. So basically rapid manufacturing technique are methods that allow designers to produce physical prototypes quickly. It consists of various manufacturing processes by which a solid physical model of a from 3D CAD model data without any special tooling. Why it is called basically rapid manufacturing? Because this is very fast and quick. Conventionally, if you want to produce something using your conventional machines, you need machine setup, you need different types of skills required to produce. You have to convert your drawings in process plan, then you have to convert, need a part program, and finally you need a prototype. Okay, to create or to develop this prototype, you need a physical system. So this physical system is basically not only time consuming, it's also cost consuming. So this new concept of rapid prototyping solve this problem by
Pradeep sir. Hello.
ठीक है ठीक है। Yeah, now I'm visible. Okay. कर लो। हाँ स्टार्ट हो गया। ओके अभी देख रहा हूँ स्क्रीन आ रही है। जस्ट शेयर किया मैंने, जस्ट हैव शेयर। अभी स्टॉप शेयरिंग। ओके नाउ शेयर ट्रे। अभी शेयर हेलो दो स्क्रीन खोले हुए हैं यार, there are two screens there. वॉइस आ रहा है मेरा? अभी देखो ना, दोनों में ओपन कर लिया है स्क्रीन से। ये कैमरा आ रहा है। ओपन सेट रे NIET नो नो presentation visible. Okay. Something is shared by another. Okay. No visible? Okay, thank you. Sorry for delay. Sorry for delay due to network issue. So the first commercial rapid prototyping process was brought on the market in 1987. As you all know, the process is SLA basically. So nowadays more than 30 different processes, not all commercialized, some are in R&D, with high accuracy and a large choice of materials exist. These processes are classified in different ways by materials used, by energy used, by lighting of prototype, photopolymers, or by typical application range. In the rapid prototyping process, the 3D CAD data is sliced into the thin cross-section plan, plus by a computer slash by software. Basically, all these processes already shared by Professor Rajkumar in morning session. I'm just go through the process. The cross-section are sent from a computer to the rapid prototyping machine, which build the part layer by layer. The first layer geometry is defined by the shape of the first cross-sectional plan generated by the computer. It is bonded to starting base and additional layers are bonded on the top of the first edit according to their respective cross-sectional plans. Means the layer by layer manufacturing is there. This process is repeated until the prototype is completed or full part is completed. This is the process flow basically for rapid manufacturing or rapid prototyping. First, we have to create the 3D solid model. To create a 3D solid model, nowadays we have a lot of options. Every college now have a different solid modeling software like SolidWorks, CATIA, Creo, NX, AutoCAD. These are the few. A lot of software available to create a 3D model. Now the 3D model technique is very easy to create a model. So once you create a 3D model, then a data preparation is there. Data preparation means you cannot use direct 3D model to this rapid prototyping machine. You have to convert in a specific format. That specific format is called the STL format. We have to convert this STL, this 3D model into STL format. Once the STL format is prepared, then we have to convert this STL format file into the different slicing. For different slicing, we need a different software called the slicing software. Once the slicing is over, slicing is nothing. It is just convert your STL file, your part file into the NC code, CNC code, 3D printing code to print or to build that part. Then the part building is started. If the part is okay, then we have to pass the part. Otherwise, part is not okay. We have to reject this part. Then we have to redesign. Then we have to recreate the solid model. Then we have to rebuild that part until we will get the desired part. Now, the requirement of this 3D prototyping basically is arise from this the concept by prototyping is required. The physical model of the product, we need a physical model of the product to test, to visualize, to assemble, to test, check. So we need a prototype basically. We need different types of degrees of this prototyping: full, complete scale model, functional model, scale model, functional and simulated material, geometrical configuration, partial model. There are different degree of prototyping we need for the before final producing that part. By this prototyping, as we already discussed, this visualization purpose, design changes, iterations is required. Free form prototyping, complex object fabrication, visualization, testing fit, packaging, cost, time and resource estimation, process planning. Critical to today's industry, the first to market, the fast approach to the market, rapid production or fast production, just-in-time concept, zero inventory concept, rapid tooling, no tooling, trend in the technology. For all of these, we need the fast prototyping system. For the design verification, we need the prototypes, design for manufacturability, design for assembly, design for maintainability, design for reliability, design for quality, design parameter, tolerances, allowances. Concurrent engineering. Concurrent engineering means this RP technology is very useful concept of concurrent engineering. Traditionally, if we want to design a part, we have to work in isolation. No consideration the manufacturing facilities available, manufacturing skills available, manufacturing machines available in the design department, or no person from the manufacturing department participate in this design process. But nowadays the concept of concurrent engineering consider the persons from all the department. So means at the design stage, the team is already known what type of facility they have, what type of material they have, and what type of skill they have that can require for convert the design into final part. So this concurrent engineering basically very useful for this rapid manufacturing, rapid prototyping technology. Now for tooling, we need reverse engineering, die fabrication, tool path generation, and if we need limited production, suppose we need a single part or 2 or 3 part or a part less than 10 or 20, we not need to set up a complete manufacturing line. Okay, to produce such type of part, this rapid prototyping technology is very useful. The rapid prototyping technology can be classified in different parameters. The subtractive process, as you know, the conventional material removal process. Example of this subtractive process like milling, turning, grinding, machining. When used for prototype production, the degree of automation is very okay. In past time, we talk about the prototype, the physical or subtractive process is used for this prototyping purpose. Okay, but nowadays the invention of this rapid prototyping system, we need the additive process, material built-up technology like stereolithography. Degree of sophistication is changed from technology to technology. Then the third process of this prototyping is the formative or sculpture, like forging, casting. When used for prototyping, it is usually a manual process. So basically, for the prototyping. But when we talk about the rapid manufacturing or the fast production, fast manufacturing, so this additive prototyping or additive manufacturing is very useful for this prototyping purpose. There's a such technology known by different terms such as this rapid manufacturing, rapid prototyping, also known as the desktop manufacturing. Because why it is called the desktop manufacturing? Because we no need of any floor, soft floor to produce the parts using this technology. A small system, say you can say just by 50 centimeter system you can put up on your decks and you can manufacture the part. That is also called the desktop manufacturing. Rapid prototyping, this is originally developed for the prototyping purpose, and the first prototyping is that's why it is called the rapid prototyping. Tool-less manufacturing, there is no need of any tool, no need of any fixtures, no need of any setup. That's why it is called the tool-less manufacturing, 3D printing. This process is somewhat similar to the printing process in 2D. Deposition of material layer by layer. That's why it is called the 3D printing. Then free form fabrication, the F3 you can say. This is the latest technology and popularly known as the FDM as well. The fabrication process. The process must take a material in some shapeless form and turn out solid object with definite shape. as you know, the fabrication process, the degree of automation. What is the degree of automation? Basically, high degree of automation is prototyping is a stage in a cycle. It is expected that the technology will enable automated chaining to the before and after links in the cycle. Ability to build complex objects. The more complex the build object, the more sophistication in the technology is required. These are the various parameters to judge the rapid prototyping technology. Then the tooling or no tooling. You can say less tools is better. One shot operations, no assembly of parts. In additive manufacturing, you no need to create the parts to create an object, different parts of a assembly. You can create a part in a single shot. No need to later assemble these parts. The less time is the better. Okay, in additive manufacturing we have less time. The closeness to serve the purpose of the prototype, accurate representation of the design. It means the accuracy of the finally product part. The flexibility, modification, addition of parameters, scaling, equipment size, weight, maintenance, economical. Both equipment and operating costs are considered for this technology. The clean and safe operation, user friendly. All these are the prototyping technology. We have to judge on the basis of these parameters. Now, rapid prototyping processes. Different types of rapid prototyping processes available nowadays, starting from the SLS, SLA, long, and FDM. These are the four prominent processes. Apart from these four processes, there are various different processes also available in the market in commercial form and in R&D form. Rapid prototyping process SLS, also known as the selective laser sintering. This process basically used to produce the part from a powder of different polymers, powder of different materials can be used to produce the final part. This technology is very useful and lead to the metal 3D printing as well. So there is a bed, as you can see, there is a bed, it's called the powder bed. A powder is spread, a metal powder is spread on that bed. And there is like a printer, you can see there is a cartridge of this powder available. Powder cartridge is available here. Okay. The powder is spread on this powder bed. And there is a powerful laser used to heating this powder basically. So when this powder is heated at the particular point, the point is scanned by a laser scanner, optical scanning system. So this point basically sintered the powder at that particular location. The sintering process, what is the sintering process basically? Sintering process, heating that powder below the melting point of this powder. There is no melting in this sintering process, and in this sintering process the powder is joining together. So by scanning the complete layer using this CO2 laser, the first layer is created, or the powder is converted into solid form joined with each other. Once the first layer is created, a roller used to labeling this first layer, then the second layer of fresh powder is spread over the first layer. Then this laser is again scan the particular section, and joining is there, solidification is there, the second layer is created. So various parameters basically useful to production of this laser sintering process. Laser power is very essential. We have to select the laser power according to the material property. The laser power will not melt the powder because the sintering process always happens below the melting point of that powder. It should not be very less, means the laser power is sufficient to convey the process of this sintering. Then the laser speed. the scanning process, basically you can say the scanning process, scanning speed is also affect the quality of this sintering process. Apart from that speed and the laser power, the diameter of this laser point is very essential. So these are the factors, these are the parameters that affect the accuracy of sintered part. There are various application range of this SLS, like visual representation models, functional and tough prototypes, cast metal parts we can create using this SLS, so selective laser sintering. There are different advantages of this technology: flexibility of materials used. You can use the PVC, nylon, sand for building, sand casting cores, metal and investment casting bags. The more advantages of this SLS is the no need to create a structure to support the part. If you work on this additive manufacturing, most of the processes require the support material. But in this SLS, there is no need of support material because the powder itself works as a support material. Parts do not require any post-curing except when ceramic is used. There is no post-processing required. The final part is accurate and finished. But in case of ceramic, we need some finishing or some post-processing in case of ceramic parts. There are some disadvantages, limitations of this SLS as well. During solidification, additional powder may be hardened at the borderline. The roughness is most visible when parts contain sloping or stepped surfaces. Now the next process is the stereolithography. This is the well-known process, and we can say this is the first process in the field of this additive manufacturing. SLS, stereolithography. SL, it is known as the SLA, basically stereolithography apparatus. Okay, the first machine produced in 1987. And this, what is this stereolithography process? In this stereolithography process, we have a laser and we have a optical system or mirror system to focus this laser on a particular location or particular point. That ultraviolet laser beam used to cure the photopolymers. This is also called the wet process. Basically, wet. What is the wet actually? Wet is nothing. It is a container where this polymer is in part. Here you can see there is a model and there is support material, support structure. You can say there is an elevator platform and liquid photopolymer tank. This liquid photopolymer tank is called the bed. Basically, that's why it is called the bed process as well. So once the laser scanned the photopolymer, the properties of photopolymer, once the ultraviolet laser scans this photopolymer, it becomes solidified due to this photopolymerization process. Once the first layer is solidified, then the elevator is down by one layer thickness. The layer thickness basically depends on the accuracy required, strength required for the part. It may be 0.1 mm, it may be 0.2 mm, it may be 0.3 mm. It depends on the vertical strength of the part required for the fabrication. So in this process, basically photopolymerization is there, and layer by layer a complete part can be produced using this laser scanning process. That's why it is called the stereolithography process. The basic polymer chemistry to produce such part by this stereolithography process. Stereolithography resin. It is a liquid photocurable resin. Liquid photocurable resin, fully 100% reactive component, energy efficient, requiring 50 to 100 times less energy than thermally pure coating. The photopolymerization is a process of linking small molecules, monomers, into large molecules, polymers, comprised of many monomers units basically. As photopolymerization occurs by chemical chain reaction, many property changes, shear strength increases, density increases, and resin changes from liquid to solid form. Shrinkage is there basically. So polymerization occurs in SL through the exposure of liquid resin to laser. The layer thickness to be polymerized is given by the amount of liquid which has been recoated onto the part, and any excess laser radiation that penetrates this layer acts to slightly increase the curing of the previous layer. The important properties for selecting the resin has to do with posture shrinkage and the resulting posture distortion. The desirable feature for this stereolithographic resin is improved impact resistance, less brittleness, greater flexibility, improved photo speed, increased strength, better overall accuracy, electrical conductivity, high temperature resistance, and solvent resistance, or vice versa. There are some distortion is there. Some measure has to taken in consideration to reduce the distortion, like use high exposure and slow scan speed. Okay, means you have to use a high exposure of resin at a slow speed of this laser, such that polymerization essentially completed under the laser spot. Use resin with a faster rate of polymerization. Okay, we have to select a resin on the basis of the polymerization process speed. Decrease laser power to decrease scan speed for a given exposure. Use low shrinkage resin. Increase layer thickness to increase the strength. There are various applications of this assay process, like parts used for functional test, manufacturing of medical models, form fit functions for assembly test. There are advantages of this assay process, like possibility of manufacturing parts which are impossible to be produced conventionally in a single process. Can be fully atomized and no supervision is required, high resolution and no geometric limitations. Some disadvantage of there, necessary to have a support structure, require labor for post processing and cleaning process. This in this assay process, support structure required and post processing process also required. That's why it is nowadays it is a very limited use for some jewelry or some dentist industry. The assay process is, otherwise other process like FDM and SLA is more prominent nowadays. The next process is laminated object manufacturing. You can say known as the LOM. The same scanning process is there, like in case of SLS, like in case of SLA, the scanning process is in LOM is same. We have to scan, but now the material has changed. In this case, in case of LOM, we have to use the sheets. It may be a paper sheet, it may be a mylar sheet, it may be a metal sheet of very thin thickness, very thin metal sheets, can be fabricated or can be developed or can be created using this laminated object manufacturing. What happens in that case? As you can see here, there is a supply roll. Okay, the one sheet is passing through that bed, and there is a scanning process. You can say the scanning process is high density laser is used to scan the part, and this scan intensity is such that it can cut that portion. Cut the cross section of this CAD design of first layer, cut that cross section and has the remaining section. Remaining section, cut that the desired part by this laser scanning. Once the first layer is created, then this supply roller used to take up the roll, and there is a fresh sheet is available above the first layer of this roll. Then the same cutting process is repeated until the final part is produced. So between these two operations, the first layer and second layer operation, there is some bonding material required to just for pasting the two sheets. There is a limited use of this laminated object manufacturing process due to the material limitations. The application range we can use this for visual representation models and large bulky models as sand casting patterns. There are different advantages of this long process, like variety of organic and inorganic materials can be used, like paper, plastic, ceramics, and composites. Process is faster than other processes. No internal stress and undesirable deformations is there. LOM can deal with discontinuities where objects are not closed completely. There are some limitations of this long process, like the stability of the object is bounded by the Strength of the glued layers. Parts with thin walls in the z direction cannot be made using loam. Okay, and hollow parts cannot be built using loam because there is no option of support material. Now the next technology, we can say the very prominent or popular technology nowadays is called the FDM, fused deposition modeling. The FDM extrusion head, as you can see on the screen, there is a FDM extrusion head. There is a filament. The filament may be of polymers material like PLA, polylactic acid, ABS, nylon, PET materials. Such type of material can be used. So this filament have various diameters. Commercial filament 1.75 mm is available and 3 mm diameter is available. On the availability of machine, configuration of machine, the 1.75 or 3 mm dia filament can be used. There is a feeding mechanism is there, a gear pulley arrangement to feed this filament to the nozzle. There is a before the nozzle there is a liquefier or hot region where this filament is heated for up to around 200 degrees centigrade depending on the different materials. The range is from you can say 180 degree to 300 degree depend on the different types of material. Like PLA we need range from 180 to 220 degrees centigrade. For ABS we need range of 120 degree to 220 degree to 260 degrees centigrade. And for different materials the range is different. So once this filament or this is liquefied due to the heating in the heating chamber, the material passing through the nozzle and deposited on the platform layer by layer. This is a simple, you can see is a commercial FDM machine, as you can see on the screen, connected to a desktop computer. This FDM process application range is used for conceptual modeling, fit form applications and models for further manufacturing process, investment casting and injection molding. Quick and cheap generation of model. These are advantage. There is no worry of exposure to toxic chemical, laser or a liquid chemical path. There are different disadvantages and restricted accuracy due to the shape of material used. Wire is around 1.75 mm diameter. Then the another process is called the material jetting. Material jetting is basically a drop on demand method. The print head is positioned above build platform. Material is deposited from a nozzle which move horizontally across the build platform. Material layers are then cured or hardened using ultraviolet light basically. There is a difference between this FDM technology and this material jetting technology. Droplets of material solidify and make up a first layer. Then platform descend or platform down by one layer thickness. In this process, good accuracy and good surface can be obtained. You can see here, this is ultraviolet curing lamp is there. Labeling platform is there. The build material is there. Support material, part support, part. So this the finishing or accuracy of this process is good as compared to the FDM process. Then binder jetting process, the glue or binder is jetting from an inkjet steel print head. Roller spreads a new layer of power on top of the previous layer. The subsequent layer is then printed and is stitched to the previous layer by the jetter binder. The remaining loose powder in the bed supports overhanging. Okay, you can see here there is a binder jetting process. A liquid binder used to bind the. This is similar to, you can say, like your printing technology. Then the other process is called the directed energy deposition. Consists of a nozzle mounted on a multi-axis arm. Nozzle can move in multiple directions. Material is melted upon deposition with a laser or electron beam. This is the basically new technology, direct energy deposition, also known as the DED. In this process, a 4 or 5 axis arm, you can say a robotic arm, can be used for this DED process. With nozzle moves around a fixed object. Material is deposited from the nozzle onto existing surfaces of the object. Materials is either provided in wire or powder form. Material is melting using a laser, electron beam or plasma arc upon deposition. Further material is added layer by layer and solidify, creating or repairing new material features on the existing object. There are different other rapid prototyping processes available, like ballistic particle manufacturing. The process uses a 3D model data to direct streams of material at a target. 3D printing creates parts by layer printing process. The layers are produced by adding a layer to powder to the top of a piston and a cylinder containing a powder bed, and the part is being fabricated. Model maker used inkjet printer technology with two heads. One deposit building material and other deposited supporting. But this is the some RP processes. As you can see, there are some parts of rapid prototyping products. Okay. This is all about the different types of processes and different technology available nowadays for additive manufacturing. But now we are at the stage of further development in this technology. If you heard that in China, a complete house is created by this 3D printing technology. A complete house completed in only 5 days using this additive manufacturing technology. Honda created a complete bike body in only 2 days by using this 3D printing technology. The R&D is going for this additive manufacturing. Still, there are some limitations of this. There are some issues that have to address. This 3D printing technology, additive manufacturing, cannot be used for the mass production purpose. If you want to use large number of parts, this technology cannot help. The research is going on to improve the speed of this process to producing the fast part in the fast pace. Nowadays, at the current research or current situation, the speed is not so much. The limitation of size as well. The commercial available 3D printers or 3D printing machines has the size limitations starting from the 100, you can say by 10 centimeters to maximum of 50 centimeters. We want to create a part, say of 1 meter. No commercial system is available to produce such type of parts. So there is need to develop bigger machines, and the material limitations as well. The research is going on to introduce different types of materials, because the technology use the laser for metal melting. You can say the laser melting process, its cost is very high. The basic machines of this metal 3D printer start from around 2 crore. It's not affordable to common man or even some small industries to produce the prototypes or final finished part. So there is need to come down the cost of these machines in affordable range. So for that, the process of this 3D printing or metal 3D printing must be changed, because the laser 3D printing is very costly. So now the different institutes, not only in India, in the world, is working on the fast and cheap metal 3D printing processes. Now a new technology known as the BAM, Buyer Arc Additive Manufacturing. Buyer Arc Additive Manufacturing technology is in the research stage nowadays. There is no commercial machine available for this BAM, but this is very useful to create the big size metal parts. In Buyer Arc Additive Manufacturing, we have to create a part by using the welding technology, like TIG, tungsten nut gas welding, MIG, or cold metal transfer. The CMT is very useful. This is the new technology of Fronius. The CMT technology is used for this BAM process. So by this BAM process, we can create large components in less time and less cost within few hours. Other 3D printing process like we have already discussed about this direct energy deposition is also used for metal 3D printing. Other research areas nowadays, if you want to do research in 3D printing, the composites. To produce the composite parts using this 3D printing. Mean the more than one materials with good strength, without any distortion. These are some research topics we have to address. This is all about from my side. If you have any query, any question, you can ask. Am I audible? Professor Rajkumar, unmute.
Hello, sir. Your screen need to share again. Actually, यहाँ पे power.
Okay. Not visible. Professor Rajkumar is visible now.
Yes, sir. It's visible.
Okay. Am I audible? Hello, Professor Rajkumar. Can you hear me?
Dr. Pradeep.
Yeah.
Sir, your slide is just showing us only the first page.
Okay. Now you can see the complete slide presentation.
Yeah, yes.
Would you have any query? Any question?
So you are done with this slide, sir?
Yeah.
Okay. So thank you so much, sir. This was such a wonderful event, a wonderful session. So we are having few queries from our participant. First query is, what is the difference between SLA and FDM?
SLA and FEM or
FDM.
FDM.
Yes, FDM.
Yeah, SLA is basically you can say selective stereolithography apparatus. Basically, SLA is known as the stereolithography apparatus, and FDM is a fused deposition modeling. The basic difference in technology. In SLA, we need a laser to cure the photopolymer. In SLA, we use the material in liquid form. But in FDM, there is no need of any laser. We have to heat the material by using a heating filament, and this is just solid. You can say the solid 3D printing process. The material in the solid form, but in the SLA, the material in the liquid form. This is the basic difference between SLA and FDM.
Another question is from another participant is that what type of different materials we can use on SLA?
SLA, basically the requirement of this SLA is the photopolymer. The material must be photopolymer and curable by a laser. Basically, this is the requirement. So any type of polymer we can use using this SLA process that can be photo cured.
Thank you, sir. Thank you for sir for this reply. One more question is there from one anonymous. He's asking, what is the full form of ABS?
ABS basically ABS is buta. You say, I'm just not remembering this name. This is a name of a polymer. I just forget the name of this. This is the butane. This is it's a type of polymer. It is not known as the.
Yeah, it's a butadiene styrene.
You may not ask about the exact name of this. I thought this ABS.
Acrylobutadiene styrene.
Yeah, exactly.
Yes, sir. Sir, thank you so much. We had a pleasant session. We had such an informative session with us. So thank you so much. We hope we will be connecting soon with few more FDPs. We will be pleased with you in those FDPs. So thank you so much, sir, for your kind presentation. And on behalf of NIT family, we are very grateful for that. Thank you so much, sir. So
thank you, Professor Rajkumar and your NIT to inviting me. It's my pleasure to share my view about this 3D printing. So thank you very much. Not only this you and NIT, all the participants, they patiently listening me. I'm just sharing my thoughts. Still, if they have any query, if they want any discussion, they are free to contact me on. I have my email ID is given.
Right, sir. We will sharing email ID with the participant. Along with that, it is displayed over the presentation here itself, and they can note it down. And for this kind gesture, and we are just moving ahead. And dear participant, you can take a break from here, and we will be assembling together again for the next session with our next speaker, honorable speaker. So